So far, we have covered various integral conservation equations of mass momentum. We have looked at certain considerations for the conservation of energy, and we have looked at non-inertial frames and all those things. But in this particular lecture, we're going to look at the differential equations which we can use to find out all the different variables in the problem. Okay, so let us start with the conservation of mass. So for a control volume which moves identically with the velocity of the fluid, the differential equation is integral, or rather the integral equation is so this is integrated over the area, this is integrated over the volume. So now we can make use of the divergence theorem and write down the second area integral as a divergence. So this becomes integral del T of rho dV over the volume plus the divergence of rho u dV is equal to 0. So then we have integral of del T rho plus divergence of rho u, this entire object integrated over the volume equal to 0. And if this statement is to be true for any arbitrary control volume, then the integrand must be 0, which implies that for a differential element inside the control volume, we can shrink the control volume to whatever you want. You can shrink it to a point. So at a given point in the flow, this is the governing equation for the conservation of mass. We have seen the different kinds of simplifications that can happen, and the simplest point is when rho equal to constant, right? Simply boils down to the divergence of velocity equal to 0. And we have also seen the situation where rho can be variable, yet we can have del rho del t plus. So if we operate this divergence operator on this, it will be u dot nabla of rho plus rho times the divergence of u equal to 0. And this entire thing becomes the total derivative of the density plus rho times this equal to 0. So we can have a flow in which the density changes in time and space such that this total derivative can vanish. If that vanishes, then it's called as variable density compressible flow. But for whatever we're going to study in this syllabus, it is sufficient to employ this as the starting point. It says that the velocity is divergence free. Coming to the conservation of momentum. Again, let us write down the statement of the conservation of momentum for a control volume which moves with the fluid. So del T of rho u dV plus integral of rho u dot n dA is equal to summation of forces, and the forces can be categorized as the surface force, which is represented by means of a traction vector, plus a body force which is represented by means of an acceleration. And the common body force that most of the flows experience is the body force of gravity, the acceleration due to gravity. And all this is written in an inertial frame. That should be clear by now. Now once again we can convert this particular term, which is an area integral, and write it in terms of a divergence. Recall that this is the momentum content and this is the flux of the flow. So this has three components, but this is a single scalar. So we can use the divergence theorem and write this down, this particular term, as the divergence of rho u dV. So on the left hand side we have del T of rho u dV plus this, And so the left hand side boils down to integral of del t of rho u plus the divergence of rho u, this entire entity integrated over the volume. On the right hand side, we have the integration of this body force over the entire volume plus the traction force. Now let us recall from our considerations of equilibrium that the traction force at a point can be represented in terms of the state of stress at that point, and depending on the orientation of the area on which the traction force is acting, the force was given as tau dot n. All right. So this particular term is equivalent to writing plus integral tau dot n dA. So the right hand side becomes integral rho g dV plus we can make use of the divergence theorem to write this area integral in the form of a divergence. But in this case, the divergence will be of the stress tensor. So finally, if this is also true and this is also true, we can write down this entire expression in terms of a single volume integral. So it will be del t of rho u plus the divergence of rho u minus rho g minus divergence of stress tensor integrated over the volume to be equal to 0. And if this particular integration is to be 0 for any control volume, the integrand must be 0, which implies that at a point the statement of the conservation of momentum boils down to this particular expression. Now let us look at how you can write down the different components of this equation. So let us write down the equation in the ith direction, or the let us write it down in the jth direction. So the first term will be del t of rho uj, that is it is the jth component of velocity, plus the divergence of, so because we are using an index notation, the divergence will become del xi rho uj ui. So the fact that u dot n cap gave rise to this divergence is captured in this repeated index I. But this j is not a repeated index, it is a fixed index. This will be equal to rho g j plus del xi of tau ij. So this is the Gurney equation. So this is the temporal term, this is the advective term, this is the body force term, this is the surface force term. All right. So let us simplify this further in the jth direction. If this is true, then we can split the first term as del rho del t uj plus rho del uj del t. The second term can be written as plus rho uj del ui del xi plus ui del xi of rho uj. This is equal to the rho Gj plus del xi of tau ij. These two terms are nothing but rho del uj del uj del t plus uj. Rather than splitting it like this, it is beneficial to rather split it in terms of this. So it will be rho uj del ui del xj plus ui. This is just for algebraic convenience. Okay, so when I take these two terms common, it will become, what is the term? Ui. There is only a certain way in which you get the best benefit out of this splitting. Let me just rewrite this. So the second term can be split as rho ui del xi of uj plus uj del xi of rho ui. Yeah, that's it. This is equal to rho gj plus del xi of tau ij. Now we can combine these two terms and write rho del uj del xt plus ui del uj del xi. We can combine these two terms and write down plus uj del rho by del t plus del xi of rho ui, while the right hand side is the same thing, it's rho gj plus del xi of tau ij. Now this particular term is the total derivative of the velocity, so this is rho duj dt. So when you expand the total derivative term, you will obtain all these terms. Now this particular term is uj multiplied by the total derivative of the density. We recall that the total derivative of any variable is del phi del t plus ui del xi of phi. So using this definition of the total derivative, you can simplify these two terms as this. Now this particular term is 0 by the conservation of mass, and so the left hand side boils down to rho duj dt is equal to rho gj plus del xi of tau ij. This particular equation is called as the Cauchy momentum equation, and it was first derived by the famous mathematician Cauchy. So what this equation says is the acceleration of the fluid element is due to the body force and the divergence of the stress, but still we do not know what are the expression for the stresses, and that particular description of the stress tensor is falling under the categorization of the constitutive behavior. This particular equation is true for any continuum. This is not just restricted to liquids, it's equally valid for solids also. But where the distinction is the constitutive behavior. For solids, constitutive behavior is a relationship between stress and strain, whereas in liquids, the constitutive behavior is a relationship between stress and the rate of strain. All right. Before that, we should quickly bear in mind that tau ij is equal to tau ji, because the conservation of momentum for a differential element is supposed to be moment free. We have already seen this at some point in our lecture. But this need not be the case for fluids which have a net couple acting on them. Now let us go towards the general description of a constitutive behavior. Let us consider a fluid at rest. For a fluid at rest, we know that the stress is isotropic and compressive. So if it is isotropic, compressive and equal from all sides at a point, so the stress must be written in the form of minus P delta Ij, where delta Ij is this. So delta Ij is an isotropic tensor. The negative sign accounts for the compressive, and minus P, which multiplies this identity matrix, is responsible for this equal from all sides. Okay, so all these properties of a stress tensor being isotropic, being compressive and equal, are embodied in this particular expression. So if tau ij is given as this, rather not if, but when the tau ij is written as this, it means that we are writing down the stress for a fluid element in equilibrium. For something which is at rest, right? Which means that P is also equivalent to the thermodynamic pressure. For a fluid which is in motion, obviously the fluid is no longer in thermodynamic equilibrium, and there will be some deviation from this particular form of stress. Alright, but before going into that, let us quickly look at what the divergence of this will be, this particular form. It will be del del xi minus P delta ij. This is minus comes outside, del del xi of P delta ij. Now the property of delta ij is such that it is equal to 1 when I equal to j, it is equal to 0 when I not equal to j. So this will be non-zero, rather it will be 1 only when I equal to j. So we set I equal to j and set this to be 1. So correspondingly, this particular I that exists over here will become del del xj of P. So it becomes minus del P del x, which means it is the gradient of pressure. So the contribution from the static component of pressure is manifested as the gradient of the pressure. And if a fluid is at rest, if the fluid is at rest, this entire left hand side becomes 0. And if that is true, we can write down the right hand side as, let us write down the three components. So 0 equal to rho. So let us write down the index equation, rho plus del del xi of tau ij, and this comes out to be rho gj minus del p del xj. So let us write it for j equal to 1. It becomes, so g1, that is the gravity acting in the x direction, is 0. 0 equal to minus del p del x. Then in the y direction, j equal to 2. 0 equal to minus del p del y. Now in the z direction, 0 equal to minus rho g minus del p del y. And the equation of motion reduces to the equation of hydrostatics. These two imply that P is not a function of x and y, it is only varying with z, due to the gravitational body force acting on the fluid.